For coming. It's a sunny day out and you're here. Thank you. And thanks to UVM. This is a wonderful building and a wonderful, this whole conference center is just terrific. So my plan today is to talk for about half an hour and then turn it over to question and answer. And the half an hour-ish presentation is a broad view of nuclear issues, and then I'm assuming that the question and answers will get more specific to the United States and to Vermont. But there's so many similarities, I figured I would take a look at the overall condition of nuclear power and how we got to where we are right now. Okay, so this is Nuclear 101, and it's a good idea to start about how a nuclear power plant starts. There's a bunch of ways of making electricity. The first way is chemically, and solar cells make electricity chemically, no moving parts. The other one is fuel cells. There's something called a Bloom box, which is about an 80% efficient process that converts a gas, methane, into electricity. So chemical processes to make electricity have no moving parts. Now there's mechanical processes. And nuclear is a mechanical process, not a chemical process. The two that I have are straight mechanical. Wind power is mechanical, and so is hydroelectric. The bicycle on the side is also a mechanical way of producing power. Basically, if you move a current, if you move magnetism through a field, you're going to create electricity. And that's what the bicycle does. Give you an idea how little power comes out of a bicycle. Lance Armstrong can generate about maybe 500 watts of power continuously for maybe 6 hours. So so a professional athlete right at the top of his performance maybe can crank out 500 watts, 500 watt bulbs for 6 hours. And then he's exhausted. Now, so 500 times 6 hours is 3,000 watts, or 3 kilowatts. Now, we pay about 10 cents for a kilowatt. So having Lance Armstrong in our basement for 6 hours, pumping on a bicycle frantically, is going to generate about 30 cents worth of power. Now, and Lance Armstrong's going to need 5,000 calories of food. So it's going to cost about $50 to feed this guy to get you but mechanical generation of power through bicycles is not recommended, that's for sure. So as long as you can get a generator moving, you're going to get electricity. So that's mechanical power. The bicycle, the hydroelectric, again, instead of having Lance Armstrong on the pedals, you're running the Winooski River so that's mechanical power. Within mechanical power is steam power. And that includes burning coal, burning oil, burning gas, and nuclear power, as well as geothermal. As long as there's a heat source involved, and you can convert that to steam, sooner or later you're going to be able to make electricity. So it's interesting. I mean, we've been burning fuels to boil water for a couple thousand years anyway. And it was just in the 1800s, end of the 1700s, when they figured out how to make a steam engine. And then, of course, steam engines evolved into steam power plants. And it's interesting, nuclear power was discovered, well, radiation was discovered about 110 years ago. Nuclear power itself was about 80 years ago. And it's the least efficient way of making electricity through steam. And we'll talk about that in a minute, but remind me that when we get back to that slide, nuclear has the lowest efficiency in converting the power into electricity of all these things. So the newest technology is actually the worst as far as the thermodynamic effects. What that means is it pumps out about 40% more heat per kilowatt into the river. So if Vermont Yankee was a coal plant, there are other issues, but as far as the heat goes, the heat from that plant would be much less than the heat from Vermont Yankee because of this inefficiency in the nuclear plant. So anyway, we've got a set of different ways of boiling water. And the last, most recent way of boiling water is nuclear, and it's the least efficient. Now, Albert Einstein had it right. He said nuclear power is one hell of a way to boil water. I checked that reference 3 times, and it's not just a one-source reference, by the way. Okay, so how does a nuclear plant work? First off, what differentiates nuclear from the others is that all the others, burning coal, burning oil, all involve a chemical reaction of electrons. They split the electrons and convert carbon into carbon dioxide. But nuclear isn't a chemical reaction. It happens inside the nucleus of the atom, hence it's nuclear. So that atom splits. A neutron, that's that little green thing on the left, collides with a uranium-235 atom and splits it in half. Now, there's a good part of that. A lot of heat is generated. And there's a bad part of it. Those 2 particles off on the side are also radioactive. And in the process, it gives off 3 more neutrons to perpetuate the reaction. So this was discovered in like 1930, and people realized, oh my God, there's about 1 million times more power generated in that reaction than there is in a comparable chemical reaction. And that's the big difference, is that pound for pound, uranium gives off an awful lot more energy than a pound of carbon. So the advantage is the heat in the middle per pound. The disadvantages are those 2 particles that float off, and we'll talk about those in a minute. So about the end of the 1930s, people realized that not only did uranium split, but it split in such a way that it could then send off other neutrons that could cause more splitting, that could cause more splitting, that could cause more splitting, and this is the nuclear chain reaction. Now, Albert Einstein recognized this in like 1938 and wrote a letter to President Roosevelt saying, you could make a heck of a bomb with this. And it's and based on Einstein's letter, the Manhattan Project began. But so a chain reaction, they discovered that a nuclear atom split in half and gave a lot of energy. And about 5 years later, they said, oh my God, we can tie these things together and it will self-perpetuate. So this is how Vermont Yankee works. There are millions of these disintegrations every second inside Vermont Yankee. So on the far side of this slide, that's occurring millions of times a second. And that's what's creating all the heat that Vermont Yankee and any other nuclear unit uses. All right, now how do you put this stuff to use? In 1954, Eisenhower had the Atoms for Peace program, and basically we knew how to make this go uncontrollably into a bomb. And the scientists said, well, we think we can control it and make a power plant out of it. And the first one was Shippingport, and then the Nautilus came by, and from there we've moved into commercial power. But it started as a military program with the Nautilus and the Navy program. But they all work the same way. This is a boiling water reactor, like Vermont Yankee. There's an extra loop in pressurized water reactors, but it's the same deal. You've got, let's start on the far left. You've got a heat source. Now, in a nuclear plant, that's a nuclear core. But if this could just as easily be McNeil Generating Station down here with its wood-burning power plant. As long as there's a source of heat, it's going to boil water. This source of heat is a nuclear reactor at low temperature steam. McNeil actually has higher temperature steam than a nuclear plant. Okay, so you've got the nuclear boiler creating bubbles, steam, that run up, and then that light blue line across the top is the steam that enters the turbine. And at this point, it's mechanical. It doesn't matter whether it's a nuclear plant or a coal plant. It's only the far left of that slide that really talks to the issue of nuclear power. It turns a turbine that's connected to a generator that sends electricity out to your house. Now, the back end of the cycle is the steam has to be condensed into water and then pumped back into the nuclear reactor to begin the cycle all over again. And there's a second loop of river water that runs adjacent to the radioactive water, but doesn't contact it directly. And that's in a thing called the condenser. And the condenser is probably twice as big as this room, and it's a pretty big, huge room. So it runs river water through one side of pipes that cools the steam and makes it water that then can be pumped back into the nuclear reactor. You can't pump steam. You need to get it back to water. So when you hear about a power plant having a condenser leak, that's river water that leaks into the condenser. The pressures are such that the river water goes into the reactor. It doesn't go the other way. When Vermont Yankee or another plant springs a condenser leak, it's dirty river water going into the nuclear reactor, not radioactive water going out into the river. There's other leaks that pollute the river, but the condenser leaks that have been endemic to Vermont Yankee are designed so it leaks in, not out. And then the cycle begins again. Let's talk about the power that comes out of that nuclear reactor. Vermont Yankee is a 650 megawatt plant, and that's roughly equivalent to 2.5 million horses, 2.5 million horsepower. And they're in a space that's 12 feet by 12 feet by 12 feet, roughly. So essentially a bedroom has 2.5 million horses of power being generated in it. And so that's the advantage, but it's also the disadvantage, as you'll see a little bit later. The beauty of nuclear compared to coal is that the power can be in a very small area. The disadvantage to nuclear compared to coal is that the power can be in a very small area. The other issue, and I talked about this about 2 minutes ago, and that's the quality of the steam. A nuclear reactor churns out steam at less than 600 degrees. The McNeil wood burner here in town has hotter steam than that, and some coal plants have steam much hotter than that. The reason is the hotter the steam, the more efficient can be the turbine. But a nuclear plant can't have hot steam because then the fuel will begin to melt. And so the problem of nuclear as far as thermal pollution goes, the nuclear plants are 40% more thermally polluting than coal, gas, and oil plants, is that they have to run them at a low temperature to prevent the fuel from melting. So that's the big difference. So again, it's fascinating to me that the newest technology, and it's 80 years old, it's hardly new technology anymore. You know, we all think of nuclear as the greatest invention on the block in the last 10 years or something. We're talking about something that was discovered in 1930 here. The newest invention in all the ways of heating water is the least efficient. Okay, so the advantages of nuclear are mainly that you get an enormous amount of power out of a very little mass. A truckload or two or three, no more than 3 truckloads of fuel are all that's required to run Vermont Yankee for a year. Now, if that were a comparable coal plant, it would be a trainload a day. So the advantage becomes the disadvantage shortly, but the advantage of having an enormous amount of power in a very small space is that it doesn't use a lot of material. Now, that doesn't mean that there are not front-end problems in this process. The uranium mining is a significant scar on the environment. And the reason there is that the quality of uranium has gradually dropped way, way down. The Belgian Congo was where uranium was initially discovered. And the ore in the Belgian Congo was close to 1% uranium. And that's what started the Manhattan Project with Belgian Congo ore. And well, that quickly got used up, and then we went down to 0.1% uranium. And now we're down at 0.1% uranium. So in a ton, the Belgian Congo ore had 2,000 pounds, kicked a decimal 20 pounds. Now we're at 2 pounds. Now we're at 0.2 pounds. And we're very rapidly heading toward 0.02 pounds of uranium in a ton of earth.